To finish the videos this week, we're talking about the differentiation of simple trig functions. This is Unit 2, Part 2, Lesson 4 of our calculus class. Looking at these two graphs, can you tell which one is the sine function and which one is the cosine function? Pause now and take a guess. The function on the left is our cosine function, and we can tell that because on the y-axis the function is at its peak and it begins to decrease as we move to the right, and it continues through its cycle. The function on the right started at the origin and is increasing through that origin, and that's an indication of our sine wave. For practice, on each of these I'd like for you to sketch the derivative. So let's focus on this cosine function, and we'll just plot the derivative right on the same set of axes. If you recall, one of the tricks that I like to use when sketching derivatives is I try to look for these points here. At each of these positions, the derivative is equal to 0 because the slope of the tangent lines at these points are equal to 0. That even happened back here too. So if each of these points correlate to a derivative that's equal to 0, then on the same set of axes, I'm going to plot the data point 0. And there we go. So we've got zeros at each of those positions. I'll clean this up and erase those marks for just a moment. Now, as I'm looking here, as we travel forward, the derivatives in this region are all negative. Every one of these slopes of tangent lines are negative through here. Now, they're barely negative at the beginning, and they're barely negative at the end, and they're steeply negative here in the middle, but they're all negative. So if I were to sketch a graph, they're getting more negative, more negative, more negative, and then they become less negative. While they're still negative, they're becoming less negative until they approach 0 again at this position. Then, as we look at the slopes of the tangent lines here, they're all positive, slightly positive, more positive, more positive. They're more steep. Less steep, less steep, less positive, less steep, until we get to the end of this section. So if we were to sketch that graph, we're starting to see this shape where the derivatives are getting higher because the slope is getting steeper to a point, and then they start getting less steep but still positive, less steep but still positive, and coming down this way. And hopefully you're starting to recognize the pattern that's being formed here, and you may even recognize this particular shape. If you've been memorizing your trig rules, this shouldn't be much of a surprise. This function in red, which happens to be the derivative of cosine, is a sine function in and of itself. The only difference is that instead of the sine function beginning at the origin and increasing upwards to begin the wave, it's actually decreasing downward to begin its wave, and that shape is indeed represented by the function negative sine of x. By the way, the slope at this position, this position, this position, the steepest slope in the cosine curve has a slope of either 1 or -1, and that's perfect because it relates directly to our sine function, where the lowest value of our sine function is equal to -1, and the highest value of our sine function is equal to +1. At this position where the slope was 1, the derivative value was exactly 1. At this position where the slope value was -1, the sine value was exactly -1. In a similar sense, we see the same thing happening over here at sine of x. At each of these flat spots on the graph, we have a derivative value of 0. So we've got all these positions where the derivative itself is equal to 0. Right here at the beginning, we had the steepest portion of the blue graph, which happened to have a slope of 1, and we've got a slope of 0, a slope of -1, slope of 0, slope of 1, and so forth. So we're again recreating in this case, the sine function. The cosine function. The derivative of sine is cosine. We're recreating that based on the steepness of all of the points along that sine function. And so that's not really a proof as to why the derivative of sine is equal to cosine and why the derivative of cosine is equal to negative sine, but I think anecdotally it gives us a good explanation why and how those are related. In a similar sense, we can do the same thing for tangent. So if this function is our tangent function, we could argue that the derivative of tangent is secant squared of x in much the same way. None of these branches or legs of the tangent function ever have a slope of 0, so none of our secant graphs, none of our derivative graphs should ever touch the x-axis. None of them are going to be 0. In fact, if I look at any one of these branches, they always have some sort of positive slope associated with it. The shallowest slope occurs right here. This is where the slope is at its least, but it's still slightly positive. So I'm just going to put a dot here. I don't know of the scaling value. I have no idea based on this graph how steep that line is, but I do know that the steepness is positive. It's greater than 0. So I'm going to plot its equivalent data point above the x-axis. As I move to the right, the slopes become steeper and more positive until we get close to this asymptote, and they're infinitely steep. So a slope that's infinitely steep would be represented by a point that's infinitely tall on the graph, and so in essence what we're seeing here is that the derivative function is increasing towards infinity as we approach this asymptote. And the same thing occurs over here. It may seem counterintuitive at first, but this is exactly what's happening. As we move further to the left, our steepness, the slope, try thinking of that slope as left to right, our steepness of each of these tangent lines was infinitely large at the beginning, infinitely steep at the beginning, and it's becoming a little bit less and less steep as we travel along. But all the time it still remains positive. So our derivative function completes or concludes this U shape. And that happens for every one of these branches of the tangent function. Now, part of the reason why I know that this is going to be a secant squared graph is because I recall that secant is actually a modified cosine function. And what used to have key data points here, 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 here. If you recall this from our Trig class last year. Oops. If you recall this from our Trig class last year, our secant function shares all the same data points as our cosine function, but anywhere that the cosine function would have struck the x-axis, that created a vertical asymptote, and wherever the cosine function was below the x-axis, that created a downward-facing U shape. Now, back to my thoughts that I was starting to say a minute ago. I know that this blue graph has to be secant because, or secant squared, because the secant function that would have existed anywhere these green U shapes were, those contain both positive and negative values. This negative value here would imply that the tangent function had a negative slope or something that was pointing downward. We don't have that. So the way to fix a function in order to require all of its results to be positive, one way to do that anyway, is to use a square surrounding it. Now here again, there is a formal proof that explains why the derivative of tangent is equal to secant squared. It's not just magic that it's secant squared, but there is a proof that supports that. That's not really the objective of this course, so we won't be covering it, but again, with this explanation, hopefully it makes a little bit of sense. These are our trigonometric functions and their derivatives, and these are the group that should be memorized. Okay, these are the ones that need to be memorized. It's only the inverse trig functions that you can bring to class on a note card. So memorize these, but bring a note card for your inverse trig functions. Let's finish out this video with some examples. We're going to include some product rules and some trig rules, but I don't think we'll see any chain rules in this particular example. Well, in this first example, we have the sum of two functions, and because of our sum rule for derivatives, I know that the derivative of y with respect 2x is going to be the derivative of each of these added together. The derivative of the sine function is cosine of x, and the derivative of the cosine function is the opposite of sine of x. Let's not forget that sign there. And to simplify this, we might write cosine of x minus sine of x. That's our derivative with respect to x. For this function here, I see a product of two functions, so we'll use the product rule, where the first function might be e to the negative x power, the second function might be sine of x. So the derivative of the first function, this is one of our, or a modified form of one of the rules that we memorized. Number 12 is what I'm referring to. E to the constant times x, e to some number times x is equal to that number times e to kx. And so in this case, k happens to be -1. In this example here, k happens to be -1. So for the derivative of e to the -1 times x, we end up with -1 times e to the -1 times x. And for our derivative of g, well, the derivative of sine, we've already said, is cosine of x. So when finding the derivative of y with respect to x, the derivative of this function, we'll multiply across this diagonal first. So I like negative e to the negative x power times sine of x. And to that we will add the products down this diagonal, which are e to the negative x times cosine of x. That's a fine answer. If you notice that e to the negative x power is a common factor, you may end up with e to the negative x power times negative sine of x plus cosine of x. That's good. Commonly, though, when we see a group of functions or a group of expressions, we tend not to lead with a negative value. So we might write e to the negative x power times cosine x minus sine of x. We can switch those because addition is commutative. Just remember to bring this negative sign along with it, along with the sine function. So that's a good answer. This is a pretty good answer too. Lastly, again, I see a product rule. We've got two functions that are multiplying together. So for the first function, I'm going to call that x, and therefore its derivative is 1. The second function I'm going to call g, which is sine of x, and we'll call its derivative cosine of x. So with the product rule here, we need dy dx to be equal to the derivative of the first function times the second function. So we've got 1 times sine of x plus x times cosine of x. Nothing really to simplify there. Now the next row does include the quotient rule, so let's practice with that too. For this first function, I'm going to call the upper function cosine of x and the lower function sine of x plus 1. So the derivative of the upper is negative sine x. The derivative of the lower is cosine of x plus 0. Again, cosine of x plus the derivative of this, which is 0. We can just call that cosine of x. So if we think of that phrase, low d high minus high d low over low low, we're again multiplying for our derivative these two first. So we want negative sine x times sine x plus 1. So that's low d high minus the high function, which is cosine, d low, which is cosine again, all over low low, or low squared, which is cosine of x squared. You'll see something interesting happen as we simplify the numerator. We've got negative sine x times another sine of x, so that's a negative sine squared of x. And the negative sine x times 1. I don't want that to look like two separate distributions. This is just one term distributing twice. So negative sine x times 1 is minus sine x. And here we have two cosines that are multiplying together, which make negative cosine of x squared. And in the denominator, we have cosine of x squared as well. Well, I happen to recognize that a number negative 1 is common to each term in the numerator. And after I factor that out, I'm left with sine squared of x plus cosine squared of x. I'm going to slide this cosine term to the left, plus sine of x. Whoops, and I just noticed a big mistake. Hopefully you caught it. Hopefully you caught it and were questioning me. Sorry about this. The denominator, the d squared, the low function, the low function was sine of x plus 1. Whoops, sine of x plus 1. Sine of x plus 1 squared, and sine of x plus 1 squared. Sorry about that. I just realized my mistake. Hopefully you caught it too. All right, so this is supposed to be sine of x plus 1 squared. Now, the reason why I grouped these two together is that we had a rule in trigonometry class that showed us that sine squared of some angle plus cosine squared of another angle always simplifies to the number 1, so that's helpful. And what we now have is a negative around the grouping symbol, 1 plus sine of x. And in the denominator, we have 1 plus sine of x squared. So here again, I didn't bother simplifying that denominator. It didn't help us, but now that it's factored, we see something that's interesting. Sine of x plus 1, when written as 1 plus sine of x, is perfectly fine, but now I've got a copy of 1 plus sine x in the numerator and a copy of it, or two copies of it, in the denominator. And what we have now is the number negative 1 over 1 plus sine of x. So we were able to take one of these expressions in the numerator and canceled it with one of the expressions in the denominator. We no longer have the square, but we do have a single copy. And so all of that work to show that the derivative with respect to x is this function. This function would allow us to find the slope at any point along this function. So that was a perfect example of why there is some benefit to simplifying the numerator, because ultimately this answer at the end is much nicer than the answer we started with at the beginning. For the rest of the video, I'd like for you to try these two examples on your own, as well as 41 and 43. You can pause the video now and resume playback in a moment to check your work. In these two examples, I first used the quotient rule for the example in the middle. And I didn't bother writing my functions off to the side this time. I just said to myself, low d high minus high d low over low. I made that, or sang that song in my head while I was working, and I was just copying the equation. Here's the low function, and I did the derivative in my head. The derivative of this, of negative sine of x, is negative cosine of x. And then the high function times the derivative of the low function all over the low function squared. After distributing in the numerator, I noticed that this negative sine x cosine of x minus another negative sine x cosine of x would cancel out, and that a negative cosine of x minus another cosine of x is the same as negative 2 cosine of x. If we were to expand this denominator, I don't think we'll see anything that will cancel. We'll be left with a collection of terms that are separated by addition signs, and we wouldn't be able to factor anything from the numerator, so I decided not to expand that, and I would say that this solution's pretty good. For this example, I was contemplating treating this as y equals cosine of x times cosine of x, and treating it like a product rule, which would have been fine. But then I realized, well, we've already talked about the chain rule, so why not utilize it? And the chain rule said take the derivative of the outer function, which is something squared, and find its derivative take the derivative of that outer function with respect to the inner function, I should say. So 2 comes down to the front, multiplied by the inner function cosine. The exponent then gets reduced to 1, which I didn't have to show. So we've got 2 cosine x, but then immediately we have to multiply by the derivative of the inner function. The inner function happened to be cosine. The derivative of cosine is negative sine. So we've got 2 times cosine times negative sine. And if we reorder that while simplifying, we can bring the negative symbol with the 2 out front. And the order of sine and cosine isn't critical. I think I tend to record sine before cosine, and that's why I made that switch. For 41 and 43, remember second order derivatives, double prime notation means to find the first derivative and then the second derivative right after it. So go ahead and pause the video and give this a try. With number 41, we're going to treat this like a product rule. First function is x and the second function is sine of x. So I use the product rule to establish the derivative. To find the second derivative of the first function, the second order derivative, I used the product rule again. However, there is a sum of 2 functions, so I didn't really need any special derivative rule to find this derivative. I just memorized that. The derivative of sine of x is cosine of x. So I only used the product rule for this component over here, and I used my first function as x and my second function as cosine of x. So the derivative of the first function and the derivative of the second function, when combined appropriately, gave me cosine of x plus x times sine of x. The 2 cosine of x's combined to make 2 cosine of x. And then the x times negative sine of x I reported as a negative x times sine of x. Now if I don't want to go through the trouble of writing the f and g functions off to the side, we can again try to do this without that side work. We can think about our keeping track of this mentally. So the derivative using the product rule says we need the derivative of the first function times the second function untouched. So we've got e to the x times cosine of x plus the derivative of the first function times the second function untouched. So we've got e to the x times sine of x. So the derivative of the first times the second, I think I said that backwards when I first did this. Let me try that again. The derivative of the first function times the second function plus the derivative of the first function times the, see, I keep screwing it up when I say it out loud. So there is a benefit to writing this down, even if you're trying to take a shortcut. The derivative of the first times the second function plus the first function times the derivative of the second function. And so we could factor this, e to the x power times sine of x plus cosine of x. Now I see the benefit here because when I need to find the second derivative, well, now I've got a product rule. I can find the derivative of this and the derivative of this and use the product rule just one time, whereas back here I would need the product rule twice to find the derivative. So let's see if I can make sense of this again. The derivative of the first function, so the derivative of the first function times the second function plus the first function times the derivative of the second function. Now the derivative of sine of x is cosine of x. The derivative of cosine is negative sine. And this answer is okay. We could find a common factor, e to the x power again, and that leaves us with sine of x plus cosine of x plus cosine of x minus sine x. These two signs will cancel, sine of x minus sine of x, and we're now left with e to the x times 2 cosine of x, which might be 2 e to the x cosine x when reported finally. I took a big gamble here and I didn't check my work on 41 and 43, so I would challenge you to do your work on your own, and if you find any discrepancies in which you're confident in your solution, if I made a mistake on mine, please correct me and I'll update this video later. Thanks for watching.